In this problem, we're taking our first look at the idea of a Laplace transform. So we're given a definition of the Laplace transform of a function of t. So we're told L of f of t is this integral where we integrate our original function f of t multiplied by a decaying exponential function. So that's e to the negative st, where s is a constant with respect to this integration. And we're integrating this whole thing on the interval 0 to infinity. So this was actually a bonus problem that I put on my last Calculus 2 exam. But the topic of Laplace transforms is usually an entire chapter in a differential equations book. So this integral transform is actually really useful for solving a lot of differential equations. But for now, we're just trying to compute the Laplace transform of sine of t, and we just want to see what it turns out to be. Now, I noted in the instructions here that the result of a Laplace transform is just a function of s. So we do the t integration with s being a constant with respect to that integration. And at the end, we come out with a function of s. And sometimes we can call that capital F of s. Now, when we start to write this down, I think it becomes clear immediately why this problem is appropriate for a second semester calculus class. First, that's an improper integral. It has an infinite limit. So we're integrating from 0 to infinity. That's not a particularly big deal, by the way. We're going to be able to handle the infinities informally. So then I set my integral up and I realized that I'm looking at an exponential function multiplied by a sinusoidal function. And this is the classic integration by parts looping trick setup. In other words, we're going to start applying integration by parts, and eventually we end up finding another copy of this original integral on the right-hand side of our work. And we're going to have to gather that together with the original integral. So I normally call that idea the looping trick. So we start using integration by parts here, and I'm going to call e to the negative st, I'm going to call that u, and then sine t dt, I'm going to call that dv. So there's our definition of u, and I need a differential of that. So du is going to be negative s e to the negative st dt, and dv again, that's sine t dt, which implies that v is negative cosine of t. So our original integral becomes u times v, so that's negative e to the negative st cosine t, and we're evaluating that from 0 to infinity, minus the integral of v du. Well, if I look at v times du, they both carry minus signs already. Those are going to cancel out, so my minus sign out in front is going to survive. And I have a constant of s tacked on to du, so I'm going to move that out in front. So I have minus s times the integral from 0 to infinity of e to the negative st cosine t dt. So at first it feels like we didn't make any progress here because the integral that we're left with is just as bad as the one we started with. But this is where we get into the integration by parts looping trick. If we define another integration by parts where we're consistent with how we did it the first time, in other words, I want to let u be the exponential piece and dv be the trig piece, then this is ultimately going to yield another copy of the original integral e to the negative st sine t, and we'll be able to gather that on the left-hand side and solve for it. And we'll go ahead and leave this term out in front as a spectator for now. We could evaluate it across the limits of integration right now, but I have a couple comments about what happens there, and I think it's a little easier to deal with if we just evaluate across the limits at the very end. So for our second round of integration by parts, we let u equal e to the negative st again, and we find du. And again, using the chain rule, that's a negative s e to the negative st dt. And then we're going to let dv be cosine t dt. And that means v is sine t this time. So we keep modifying our original integral. Note that implicitly on the left-hand side of this equal sign is our original f of s. So we have this term that is just a spectator, negative e to the negative st cosine t evaluated from 0 to infinity. So we're going to get back to that in a second. And then we have minus s times this integral that I'm doing with integration by parts. So I take u times v, that's an e to the negative st sine of t, and evaluate from 0 to infinity, and then minus the integral of v du. Well, this time v times du has a net minus sign in it, so I can pull that out in front and I get a positive result. We could also factor out an s. So I end up with a plus s integral from 0 to infinity, e to the negative st sine t dt. And there's our original integral. So I still have to distribute this negative s. And on the right-hand side of our equation here, we have a minus s squared times the original integral. We also have this piece that's being evaluated across the limits of integration. That's going to be a negative s e to the negative st sine t. So with a minus s squared times the original integral, I can go ahead and add that to both sides. And I end up on the left-hand side with an f of s. We're just going to use that name for it so it's more compact. That's the original integral plus an s squared f of s. Again, f of s is just the integral of e to the negative st sine t dt. On the right-hand side, we have these leftover pieces that need to be evaluated. So that's a negative e to the negative st cosine t from 0 to infinity. And we have a minus s e to the negative st sine t on 0 to infinity. So let's go ahead and evaluate all that stuff on the right-hand side. I don't encourage my students to use formal limits for this because subbing in the infinities is unambiguous. If I sub in an infinity to this first one, well, the cosine function is bounded between -1 and 1. That always stays finite. But I have a decaying exponential out in front. Now, if that constant s is greater than 0, that exponential is going to crush this thing to 0. So e to the negative infinity is unambiguously 0. So I get a 0 out of that upper limit, again, provided s is greater than 0. When I subtract the lower limit there, I'm going to get a positive term, and I'm subbing in t equals 0. Well, e to the 0 is 1, and cosine of 0 is 1. So I end up with a positive 1 out of that term. Let's see what happens in the second term. Again, for the case that s is greater than 0, if I sub in the infinity there, I get e to the negative infinity multiplying a function that's bounded between -1 and 1. So again, that unambiguously goes to 0. Then when I subtract my lower limit, well, subbing in t equals 0 gives me an e to the 0 times the sine of 0, which is 1 times 0. Remember, the sine of 0 is 0. So both terms are 0 this time. Again, this only works if we restrict our values of s to being positive. Note that I kind of ignored an edge case here, like what if s is actually equal to 0? If s is equal to 0, then it looks like the Laplace transform is trivial. It's just the integral of the original function on 0 to infinity. And the integral of sine t on 0 to infinity never converges. It just keeps oscillating because the sine function just keeps bouncing between -1 and 1. So anyway, that's the s equals 0 case. That's not going to converge either. All right, back to the left-hand side, we can do a little factoring here and write it as 1 plus s squared times the original function f of s. And now we simply have to divide by 1 plus s squared. And we find that the Laplace transform of sine of t is just 1 over 1 plus s squared, provided s is greater than 0. So if you're curious to learn more about Laplace transforms, there's normally an entire chapter dedicated to this in an introductory differential equations book. This is actually a really beautiful tool. So what we do is transform entire differential equations into this Laplace transform S space. And then basically what happens is the solution of the differential equation comes down to algebra in S space. You find the solution there, and then you transform back into ordinary T space. And this is just a really beautiful prototype for the character of mathematical physics in general. Like that shift into S space is just a radical change in perspective that renders all the mathematics trivial. And then you solve your problem in that weird abstract space, and then you just transform your solution back to the real world. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.